Let's look back at some of the historical developments that led to our current understanding of the atom. Everything in our lives, everything in the whole universe, is composed of atoms. If you want to understand matter, you must begin by understanding atoms. The theory that all matter is composed of atoms arose primarily out of three laws developed by scientists in the late 1700s. These laws look really simplistic to us now after more than 200 years of scientific developments, but at the time, these laws provided new insight into how matter behaved. Try to imagine for a minute that you don't know about the existence of atoms. As a scientist at the end of the 18th century, you're studying the macroscopic behaviors of matter, the visible, the measurable behaviors of a sample, and you're trying to interpret what these behaviors might mean about the microscopic level structure of matter. You're using something you can see to try to figure out something you can't see. First, in 1789, Antoine Lavoisier formulated the law of conservation of mass that says, in a chemical reaction, matter is neither created nor destroyed. For example, if 7.7 grams of sodium reacts with 11.9 grams of chlorine gas, that's a total mass of 19.6 grams. Then 19.6 grams of sodium chloride will be formed. This behavior suggested to scientists of the time that matter might be composed of small, indestructible particles. In 1797, Joseph Proust developed the law of definite proportions. All samples of a given compound have the same proportions of their constituent elements. For example, that means 18 grams of water is always composed of 16 grams of oxygen and 2 grams of hydrogen. Any sample of pure water from any source will always have an oxygen to hydrogen mass ratio of 8:1. Third, in 1804, John Dalton published the law of multiple proportions, which says when two elements form two different compounds, the masses of one element that combine with 1 gram of the other element can be expressed as a small whole number ratio. For example, carbon and oxygen can combine in multiple ways, including the compounds carbon dioxide and carbon monoxide. For every 1 gram of carbon in carbon dioxide, there's 2.67 grams of oxygen. In carbon monoxide, there's 1.33 grams of oxygen for every gram of carbon. The ratio of these two masses of oxygen, 2.67 to 1.33, is a small whole number, 2. Again, as with the law of conservation of mass, this suggested to scientists that matter came in discrete particles that could combine together to make compounds. At the time, Dalton already suspected that matter was made of atoms. To him, the law of multiple proportions said that an atom of element A could combine with 1, 2, or 3, or more atoms of B to make various compounds. But an atom of A never combined with half an atom of B, or 2/3 of an atom of B. Shortly thereafter, Dalton formalized his ideas into a 4-part atomic theory. He said, 1. Elements are composed of indivisible particles called atoms. 2. Atoms of the same element are identical. Atoms of different elements are different. 3. Atoms can physically mix or chemically combine in simple whole number ratios. And 4. In chemical reactions, atoms can separate, join, or rearrange. Atoms of one element cannot become atoms of another element. Dalton's atoms could affectionately be thought of as bowling ball atoms. He saw atoms as tiny, indestructible spheres, solid, and uniform internally. The sphere was unique in some way from one element to the next. Compounds were spheres of multiple elements stuck together somehow. That was Dalton's view of atoms. It was nearly 90 years before the next big advance in atomic theory. In 1897, J.J. Thomson used a cathode ray tube to study various gases. For every gas tested, a stream of particles, which he called a cathode ray, moved from the negative to the positive plate. This led Thomson to propose the existence in all atoms of a negatively charged particle, which we now call the electron. Thomson was able to measure the charge-to-mass ratio of the electron using electric and magnetic fields and observing the deflection of the stream of particles. He did this by measuring the strengths of the electric and magnetic fields that canceled exactly, leaving the stream of charged particles undeflected. He was not able to determine the charge or the mass individually. From his discovery of the electron, Thomson developed a new model of the atom. Atoms were no longer little bowling balls with no internal structure. Atoms contained electrons. Thomson proposed that atoms were spheres of positively charged material with the negative electrons dotted throughout. This model was referred to as the plum pudding model, in reference to a common dessert of the time. Today, his model could be imagined as the blueberry muffin model. The blueberries are the electrons and the dough is the positively charged material. 12 years later, American scientist Robert Millikan was able to determine the charge of the electron using an oil drop experiment. In his apparatus, an atomizer produced super small drops of oil in the upper chamber. These tiny drops were allowed to fall through a small hole into a lower chamber where radiation was used to charge up the oil drops with electrons. So the oil drops are now negatively charged. The lower chamber has a positively charged plate on top and a negatively charged plate on bottom. Negatively charged plate repels negatively charged oil drops. So gravity is pulling the oil drops downward. The electric charge on the plates attempts to stop the downward fall of the drops. Millikan would vary the strength of the electric field between these plates and observe the effect on the speed at which the oil drops fell. As he increased the strength of the electric field, the oil drops would slow in their descent. Millikan could even reverse the fall of the drops. He could make them move upward by increasing the strength of the electric field enough. Millikan measured the strength of the electric field required to halt the free fall of the drops. He used this value and the calculated masses of the drops to calculate the charge of each drop. Millikan repeated this experiment for many, many droplets. The calculated charges for all those droplets were all multiples of some fundamental value, which Millikan calculated to be negative 1.60 times 10 to the negative 19 coulombs. This, then, was the charge of a single electron. In 1911, Ernest Rutherford, a student to J.J. Thomson, designed and performed an experiment attempting to confirm Thomson's plum pudding model of the atom. Rutherford shot a beam of positively charged alpha particles at an ultra-thin sheet of gold. He surrounded the sheet of gold with a detector plate that signaled the location of the alpha particles after contact with the gold foil. Based on Thomson's plum pudding model of the atom, Rutherford expected to see the alpha particles pass through, largely undeflected. Thomson's model had a very uniform composition. The alpha particles should be able to push right through it. Rutherford did observe many alpha particles pass straight through the gold foil, but he also saw that some alpha particles were deflected at large angles, sometimes straight back toward the alpha source. This result could not be explained by Thomson's model of the atom. Rutherford was forced to propose a new model. For positive alpha particles to have been deflected, Rutherford proposed that the gold atoms must have a concentrated area of mass and positive charge inside them. Even though the gold foil appears completely uniform on the macroscopic level, Thomson's uniform atoms are not correct. Matter is not so uniform at the atomic level. An atom is a lot of empty space with a small, dense core. From this, Rutherford proposed the nuclear theory of the atom. First, he named the small core of mass and positive charge a nucleus. Second, he stated that most of the volume of an atom is empty space, throughout which tiny negatively charged electrons are dispersed. Many students struggle with the idea that we are made of atoms that are mostly empty space. The floor of your bedroom is made of atoms that are mostly empty space. How can something be solid if it's mostly empty space? The key to resolving this conflict is an understanding of scale. Atoms are incredibly small, so the amount of empty space in each atom is also incredibly small. Here's a fair analogy. Imagine a huge scaffolding or the metal frame of a skyscraper before the exterior is added. Up close, that scaffolding is clearly mostly empty space. If you view the scaffolding from an airplane, though, it would look solid. If we were as small as atoms, we could observe the empty space in each atom, like viewing the scaffolding up close on the same scale as our own bodies. But our view of atoms is more like the view of the scaffolding from outer space. From that distance, the scaffolding is far too small for us to observe the empty spaces. The same goes for atoms. Atoms are far too small for us to observe the empty spaces. The third part of Rutherford's nuclear theory of the atom says that atoms are electrically neutral, so there's the same number of positive protons in the nucleus as there are negative electrons outside the nucleus. Although Rutherford's model was highly successful, scientists realized that it was incomplete in two important ways. One, what are the electrons doing? Opposite charges attract each other, just like opposite ends of two magnets. So, negative electrons should be attracted into the positive nucleus. How do the electrons stay out of the nucleus? The second problem is with the mass of the atom. Protons can't account for all the mass of the atom. Where's the missing mass? Let's discuss the first issue first. Niels Bohr addressed the first issue when he suggested that electrons stay out of the nucleus by adopting fixed pathways called orbits around the nucleus, in the same way that planets orbit the sun without ever falling into the sun. Bohr said that only orbits of certain energies were allowed, and that electrons can jump from one orbit to another by absorbing or emitting a specific amount of energy. While Bohr's idea of electron orbits, actual paths that the electrons must follow, was quickly proven incorrect, scientists still use the main idea of his model to discuss many properties of atoms. The idea that electrons exist in concentric shells around the nucleus is oversimplified, but not entirely wrong. Erwin Schrödinger is given primary credit for developing our current model of the atom, which gives a better description of the placement and behavior of the electrons in the atom. This is referred to as the quantum mechanical model or the electron cloud model. In the quantum mechanical model, electrons are not located in exact pathways. Instead, mathematical equations define areas of space around the nucleus where electrons might be found. These regions of space are called orbitals. Later in the school year, we'll come back and discuss the quantum mechanical model in great detail. For now, we're going to stop at an understanding that electrons do not travel in pretty circular orbits around the nucleus. The quantum mechanical model defines, instead, regions of space around the nucleus, called orbitals, where electrons might be found. That is our current understanding of the electrons in atoms. Recall from earlier that the second problem with Rutherford's model of the atom dealt with missing mass. Scientists realized early on that the protons could not account for all the mass of the atom. If hydrogen has 1 proton and helium has 2, and the protons did account for all the mass of an atom, then helium should have a mass twice that of hydrogen. Instead, helium's mass is 4 times greater than hydrogen's. Rutherford actually suggested the possibility of what he called a neutral proton, and just such a particle was discovered by one of Rutherford's students named James Chadwick, but the particle wasn't discovered until 1932. The particle, as we know it, is named a neutron. The mass of a neutron is indeed very close to that of a proton. Neutrons differ from protons in that they carry no charge. So now we can answer the question about the mass of helium versus hydrogen. Helium has 2 protons, hydrogen has 1. But helium also has 2 neutrons that contribute to its mass. We know that all atoms are composed of the same subatomic particles, protons, neutrons, and electrons. Protons and neutrons have nearly identical masses, while the electron's mass is 1/1840th that of a proton. Electrons are effectively massless. The charge of the proton and the electron are equal in magnitude but opposite in sign, and neutrons carry no charge. The most important number to the identity of an atom is the number of protons in its nucleus. The number of protons defines the element. If a nucleus contains 2 protons, it's a helium atom. If a nucleus contains 6 protons, it's a carbon atom. The number of protons in an atom's nucleus is called its atomic number. The symbol Z is used to represent atomic number. The number of protons and neutrons in the nucleus is called the mass number. For example, for a helium nucleus, the atomic number is 2 because there are 2 protons present. The mass number, the total number of protons and neutrons, is 4.